Few things in the universe feel more unknowable than a black hole. And yet, somehow, we can still trace what would happen if you fell into one. Not just the equations or the abstract physics, but the actual experience. What you would see, what you would feel, how the universe would look as you crossed a boundary from which nothing returns. It's a journey no one has taken, and yet, using the mathematics of space-time and gravity, we can trace parts of it, step by step, at least as far as our current understanding allows. You're listening to the Drowsy Astronaut. Over the next while, we're going to take that journey together, slowly and carefully, beginning at a safe distance and moving inward through the strange geometry of curved space-time and into regions where our physics begins to fail. This is a slow, relaxing voyage into one of the universe's deepest mysteries. If you're listening from bed, from a quiet room, from anywhere you've settled in for the night, you're exactly where you need to be. Feel free to let us know in the comments where you're listening from. We love hearing from you. And if you enjoy these slow cosmic journeys, a like or subscription helps us keep making them. But for now, just get comfortable, and whenever you're ready, we'll begin. Let's say you're falling toward a black hole, not being pulled against your will, not in distress, just falling, moving through space toward an object unlike anything else in the universe. The black hole is alone, isolated, far from any star or planet, surrounded only by the distant light of galaxies and the depth of empty space. You're approaching from a distance, moving inward, and the first thing you notice is not the black hole itself, but the absence it creates. Against the backdrop of stars, there's a region where no stars shine. It's perfectly round, or nearly so, a circle of absolute darkness, expanding slowly in your field of view. The stars around it are still visible, scattered across space in all directions, but within that circle, nothing. No light, no glow, no hint of structure, just black. The void is so complete that it feels less like an object and more like a hole in the sky. A place where the universe has been cut away. As you drift closer, the circle grows. It's not rushing toward you. The approach is steady, almost gentle, but it's undeniably growing, consuming more of your view. The stars at its edge don't simply disappear. They bend. Light from stars directly behind the black hole, stars that should be hidden from view, curves around the black hole's immense gravity and reaches your eyes. You see those stars not where they actually are, but displaced, distorted, smeared into arcs and curves around the edge of the darkness. This bending of light is called gravitational lensing. The black hole's gravity is so strong that it warps the fabric of space-time itself, and light, which travels along the curves of space-time, follows those warps. A star directly behind the black hole appears as a ring of light encircling the dark circle, a perfect Einstein ring if the alignment is exact. Stars, slightly off to the side, appear stretched, elongated, duplicated in some cases. The effect is subtle at first, just a slight distortion, but as you move closer, it intensifies. The edge of the black hole is not sharp. There's no physical surface there, no boundary you can touch. What you're seeing is the photon sphere, a region where gravity is strong enough that light can orbit the black hole. Photons, particles of light, circle endlessly at this radius, trapped in unstable orbits. Some of that light escapes outward, some falls inward, and the boundary between the two creates a faint glow around the black hole's silhouette. It's not bright, nothing like the blazing accretion disks you might imagine from illustrations. This black hole is quiet, isolated, without an accretion disk. The only light is from the distant stars, bent and focused by gravity. You continue to fall. The darkness grows, and the distortions intensify. Stars that were once directly ahead of you now appear shifted, move toward the edges of your vision. Stars behind you remain visible, but their light is bending around the black hole, reaching you along curved paths through space-time. Your field of view begins to change in strange ways. The stars ahead, in the direction you're falling, seem to compress into a smaller and smaller region. The stars behind and to the sides spread out, filling more of your peripheral vision. The universe is being reshaped by gravity. The black hole itself remains dark, perfectly dark. No light escapes from within the event horizon, the boundary beyond which even light cannot climb back out against gravity's pull. You haven't reached that boundary yet. You're still outside, still in a region where light can escape, where you could, in principle, fire rockets and halt your fall. But you don't. You continue inward, and the darkness grows. From this distance, the black hole reveals almost nothing about itself. You can't see its mass directly, can't observe whether it's rotating or stationary, can't measure its temperature or its age. All you see is the absence, the silhouette, the gravitational shadow it casts against the stars. Black holes have been described as having no hair, a phrase physicists use to mean that they're remarkably simple objects. Once formed, a black hole is defined by only three properties: mass, rotation, and electric charge. Everything else, the composition of the star that collapsed, the details of its structure, the history of its formation, is erased. What remains is pure gravity, pure space-time curvature, described completely by those three numbers. The black hole you're approaching is moderately sized by cosmic standards, perhaps 10 times the mass of the Sun. It formed from the core of a massive star that exhausted its fuel, collapsed, and exploded as a supernova, leaving this dense remnant behind. The event horizon, the boundary of no return, is about 30 kilometers in radius. That's small, roughly the size of a city, and yet it contains 10 times the mass of an object 1 million kilometers wide. The density is beyond comprehension, but you don't perceive density from out here. You perceive only gravity, only the bending of light and the pull drawing you inward. There's something calming about the approach, despite the strangeness. The fall is smooth, almost serene. You're weightless, in free fall, experiencing no force, no acceleration you can feel. Gravity pulls every part of your body equally, so there's no sensation of being pulled. If you closed your eyes, you might not know you were moving at all. Only the changing view tells you that you're falling, that the black hole is growing, that the stars are shifting. The distortions continue to build. The circle of darkness now occupies a significant portion of your view, and the stars around it are noticeably warped. Some stars appear in multiple places, their light having taken different curved paths around the black hole to reach you. The images overlap and blur slightly, creating a strange doubling effect. The photon sphere, that faint bright ring around the edge, is more visible now, a delicate halo of starlight focused by gravity. You pass through the photon sphere. From inside, the view changes again. Light that was orbiting the black hole, trapped in unstable circles, now spirals inward with you, or escapes outward, and the faint glow shifts. The darkness is closer now, more immediate. The stars ahead have compressed into an ever-shrinking circle, while the stars behind have spread across the sky, filling your peripheral vision and curving around behind you. It's as if the entire universe is rotating, wrapping itself around the black hole. The event horizon is below you, or ahead of you. Direction becomes strange near a black hole. You're falling toward it, and it's rising up to meet you. A boundary defined not by space, but by the geometry of space-time itself. It's still invisible, still just a concept, a mathematical surface. But it's there, and you're approaching it quickly now. The stars continue their strange dance. The light from distant galaxies, bent and distorted by the black hole's gravity, paints arcs and streaks across the darkness. The view is hypnotic, constantly shifting as you fall. You are moving through a region where space-time itself is curved so severely that straight lines no longer exist. Every path, every trajectory is bent toward the center. And yet, despite the strangeness, despite the knowledge of what lies ahead, the fall remains quiet. There's no sound in space, no wind, no friction, just you, weightless, drifting inward, watching the universe transform around you. The black hole is below, vast and dark, and the stars are above and behind, distant and distorted. The journey has only just begun. The event horizon is not a place you can point to and say, there, that's where it is. It's a boundary in space-time, a surface defined by gravity's strength, by the point at which escape velocity equals the speed of light. Inside that boundary, all paths, every possible trajectory lead inward. Outside, escape is still possible. The horizon itself is simply the dividing line between those two regions, and it has no physical substance, no wall, no membrane, no structure, just geometry. You're approaching it now, falling faster, though you still feel nothing. The darkness below is vast, filling most of your view. The stars behind you, above you, to your sides, are compressed into a shrinking circle of light, a tunnel of luminous distortion against the black. The curvature of space-time is so extreme here that light from the outside universe is being focused, bent into increasingly tight arcs. The effect is beautiful in a strange, impersonal way, like looking through a lens that warps everything beyond recognition. The event horizon of this black hole, 10 solar masses, has a radius of about 30 kilometers. That's measured from the center, from the singularity deep within. The circumference of the horizon is about 190 kilometers, a distance you could walk in a few days under normal circumstances. But here, space is curved, and distances don't mean what they usually mean. The horizon is approaching, or you're approaching it, and the distinction hardly matters. In your reference frame moving inward, the horizon is simply ahead, a boundary you're about to cross. From your perspective, there's no indication of exactly when the crossing happens. The view doesn't change suddenly. The stars don't blink out. There's no flash, no sensation, no marker. You simply pass through an invisible surface, and in that moment, something profound shifts, though you don't feel it. You are now inside the event horizon. Every possible future, every path through space-time you could take, leads deeper inward. Turning around is no longer a matter of choice, or thrust, or energy. The singularity is not a place you're moving toward. It's a moment in your future, unavoidable, written into the geometry of the space-time you now occupy. But from your perspective, nothing dramatic has happened. You're still falling, still weightless, still watching the stars. The transition was smooth, almost disappointing in its lack of ceremony. You crossed the most famous boundary in physics, and it felt like nothing at all. That smoothness, that lack of drama, is one of the strangest aspects of black holes. The event horizon is absolute. Once crossed, return is impossible. And yet, locally, at the moment of crossing, space-time is only mildly curved. For a large enough black hole, you could cross the event horizon without even realizing it, without experiencing any strong tidal forces, without any change to the view or the sensation of freefall. The extremity is global, not local. It's in the topology of space-time, in the fact that all future paths converge inward, not in any immediate physical effect, but while you experience nothing unusual, an observer watching you from a safe distance sees something very different. To them, you never cross the event horizon. Not ever. As you approach the boundary, your image appears to slow down. Time dilation, the stretching of time in strong gravitational fields, becomes more and more extreme as you near the horizon. To the outside observer, seconds for you appear to take minutes, then hours, then years. Your light becomes redshifted, the wavelengths stretched by gravity, and you fade from view, dimming gradually into infrared, then radio, then nothing. You appear to freeze just above the event horizon, an image suspended in time, asymptotically approaching the boundary, but never quite reaching it. From their perspective, you never fall in. From your perspective, you cross quickly and continue inward. Both perspectives are correct. Both are valid descriptions of reality, according to general relativity. This is not a contradiction, not a failure of the theory, just a consequence of how space-time and observation work near extreme gravity. Time is relative. What happens now depends on where you are and how you're moving. For you, crossing the horizon happens at a specific moment. To the outside observer, it never happens at all. Or rather, it happens infinitely far in their future. This paradox has deep implications. If no outside observer ever sees you cross, in what sense do you cross? If the universe outside continues to evolve, stars burning out, galaxies colliding, while you fall, do you see that future as you descend? The answers depend on perspective and on subtle details of how light behaves near the horizon. Questions we'll return to shortly. For now, you're inside, moving inward, and the view continues to shift. The stars, already compressed into a bright ring behind you, appear even more concentrated. Light from the outside universe is still reaching you, streaming inward across the event horizon. The horizon doesn't block light from coming in, only from going out. Photons that entered before you, or that enter now from the outside, can still catch up to you, can still reach your eyes. The universe outside is still visible, still bright, but it's confined to an ever-shrinking region of your visual field. Ahead of you, in the direction of your fall, there is only darkness. No light escapes from deeper within the black hole to reach you. Any light that was emitted inside the horizon is also falling inward toward the singularity, and it cannot move outward relative to space-time, cannot catch up to you from below. The darkness is absolute, a void that reveals nothing of what lies ahead. The geometry of the horizon itself is worth considering. For a non-rotating black hole, a Schwarzschild black hole, the event horizon is a perfect sphere. Every point on it is equivalent to every other point. There's no north or south, no structure, no variation. It's a pure geometric surface in space-time, defined entirely by the radius at which escape velocity equals the speed of light. Time and space behave strangely at this boundary, in ways that are difficult to describe without mathematics. But the essential fact is simple. Crossing it is a one-way transition. For a rotating black hole, which we'll explore later, the horizon is slightly different. It's oblate, flattened at the poles, and there are additional structures, the ergosphere, the inner horizon, that complicate the picture. But the basic principle remains. The event horizon is a point of no return, a boundary in space-time beyond which all futures lead inward. You continue to fall, now on the inside, and the pull of gravity continues to accelerate you. You're moving faster, not because you're being pushed, but because space-time itself is structured such that staying still is no longer possible. Inertia, the tendency of objects to move in straight lines through space-time, now carries you inward. The straight line, the geodesic you follow, points toward the center, toward the singularity. There's a strange inversion that occurs inside the event horizon, one that's often described but difficult to truly grasp. Outside the horizon, the singularity is a place, a point in space at the center of the black hole. You could, in principle, avoid it by accelerating, by changing your trajectory. Inside the horizon, the singularity is no longer a place. It's an event, a moment in time, in your future. Avoiding it would be like trying to avoid tomorrow. The mathematics of general relativity show that time and the radial direction swap roles at the horizon. Outside, you can move toward or away from the center. Inside, you can only move forward in time. And moving forward in time means moving toward the singularity. This is abstract, difficult to visualize, but the consequence is concrete. You cannot stop, cannot turn around, cannot wait. The singularity is coming, not in space, but in time, and it will arrive in seconds or minutes, depending on the mass of the black hole and where you are in your fall. But the singularity is still ahead, still in the future. For now, you're falling through the region just inside the event horizon, a place where space-time is curved, but not yet catastrophically so. The stars are still visible behind you. The darkness is still ahead. The journey continues, quiet and strange, into the unknown. Time is one of the first things to become strange when you approach a black hole. Though the strangeness is subtle, easy to miss if you're not paying attention. From your perspective, falling inward, time flows normally. Your watch ticks at its usual rate, 1 second per second. Your thoughts progress in the familiar sequence. Your heartbeat, your breathing, the firing of neurons, all continue as they always have. There's no subjective sense that time has changed. You are your own clock, and your own clock always runs at the same rate, no matter where you are or how fast you're moving. But time as general relativity describes it, is not absolute. It's woven into the fabric of space-time, and gravity warps that fabric. The stronger the gravitational field, the more slowly time passes relative to regions of weaker gravity. This effect, called gravitational time dilation, is real and measurable. GPS satellites have to account for it, adjusting their clocks because time runs slightly faster in orbit than it does on Earth's surface. Near a black hole, the effect becomes extreme. Imagine someone far from the black hole, floating in nearly flat space-time, watching you fall. To them, as you descend toward the event horizon, you appear to slow down. Not because you're decelerating, not because anything is resisting your fall, but because time itself, from their perspective, is passing more slowly for you. Every action you take, every movement, every signal you send, takes longer to occur from their point of view. If you were shining a light toward them, the pulses of light would arrive at longer and longer intervals, stretched by the gravitational field. As you approach the event horizon, this time dilation becomes infinite. To the outside observer, you asymptotically approach the horizon, your motion slowing toward stillness, your image freezing in place. Your light becomes redshifted, the photons losing energy as they climb out of the gravitational well. Red light shifts to infrared, infrared to microwave, microwave to radio. Eventually, the wavelength becomes so long, the energy so low, that the light is undetectable. You fade from view not because you stopped emitting light, but because the light has been stretched beyond observation. From your perspective, none of this happens. You fall toward the horizon and cross it in a finite amount of your own time. Perhaps a fraction of a second for a stellar mass black hole, perhaps a few seconds or minutes for a more massive one. The horizon doesn't slow you. You don't freeze, you simply cross, smoothly and quickly, and continue inward. This creates a profound asymmetry. From your perspective, the outside universe continues to exist, continues to evolve. Stars burn, planets orbit, light travels through space. But to the outside universe, you have essentially left time. You have reached a point in their far, perhaps infinite future, a moment that never quite arrives from their frame of reference. Both views are true. General relativity doesn't privilege one perspective over the other. Time is relative, dependent on the path you take through space-time. There's another consequence of this time dilation that's less often discussed, but equally strange. If you could somehow look back at the outside universe as you fell, you might expect to see time passing more quickly out there. Just as they see your time slowing, you might see their time speeding up. And indeed, this effect does occur. Light from the outside universe, falling inward with you, becomes blue-shifted rather than red-shifted. The wavelengths compress, the energy increases. Events that would take years in the outside universe might appear, in principle, to unfold more quickly from your accelerating reference frame. In practice, the effect is complicated by the bending of light, by the specific trajectory you're following, and by the fact that light takes time to reach you. You don't see the entire future history of the universe play out in an instant. The blue shift is gradual, and the light you see is still from the past, just less deeply in the past than it would otherwise be. But there's a real sense in which, as you fall, the universe outside ages relative to you, even though your own time proceeds normally. Gravity, meanwhile, is not something you feel directly in free fall. When you're falling freely, weightless, you experience no force. Gravity is not a force in the traditional sense, not in general relativity. It's the curvature of space-time, and objects in freefall are simply following the straightest possible paths through that curved geometry. You don't feel the pull of the black hole any more than you feel the pull of Earth's gravity when you're in orbit. What you would feel, if anything, are tidal forces, the differences in gravitational pull across your body. But we'll come to those shortly. The strength of gravity, the degree of space-time curvature, increases as you descend. Outside the black hole, far from the event horizon, space-time is only mildly curved. The distortions are small, the bending of light subtle. Closer in, the curvature intensifies. Distances stretch, time dilates, light bends sharply. At the event horizon, the curvature reaches a critical threshold, where the escape velocity equals the speed of light. Inside, the curvature continues to grow, steeper and steeper, until it becomes infinite at the singularity. But curvature, like time, is not something you perceive directly from inside the experience. You don't see space-time bending. You see the effects, the distortion of starlight, the compression of the universe behind you, the darkness ahead. The curvature is encoded in those effects, in the paths light takes, in the way distances and durations relate to each other. You continue to fall, and gravity continues to accelerate you. Your speed, measured relative to the local space-time, increases. If you were to drop an object, it would fall alongside you, weightless, because you're both in free fall. But if you were to measure your speed relative to something stationary far from the black hole, if such a measurement were even meaningful, you'd find that you're moving faster and faster, approaching the speed of light as you near the singularity. Not because you're being pushed, but because the geometry of space-time channels all motion inward. Time and gravity, space and motion, all of these concepts blur together near a black hole. The clear distinctions we make in everyday life. This is space, this is time, this is up, this is forward, become ambiguous. Space-time is a single structure, and extreme gravity reveals its unified nature. The equations of general relativity describe this beautifully, precisely, but translating those equations into experience, into what you would see and feel, requires careful thought. What's clear is this: from your perspective, time is normal, gravity is invisible, and the fall is smooth. From the outside perspective, you have slowed to a stop, time dilated into an eternal descent, never quite crossing the horizon. Both are true, both are real. The universe is not required to make sense from a single point of view. Light is the messenger by which you perceive the universe. And near a black hole, light behaves in ways that transform what you see. Photons travel in straight lines, or, more precisely, they follow geodesics, the straightest possible paths through space-time. But when space-time is curved, those geodesics curve with it. Light bends around massive objects, and near a black hole, where the curvature is extreme, light bends sharply, loops, and even orbits. You're inside the event horizon now, falling inward, and the light reaching you comes only from outside the black hole. No light is being emitted from within, because any light emitted here is also falling inward, moving toward the singularity just as you are. The only photons you can see, are those that entered the event horizon from the outside universe, either before you or alongside you, and are now catching up or accompanying you on the inward journey. The stars, the galaxies, everything outside, all of it is still visible, but only in a specific direction. Behind you, or rather in the direction away from the singularity, a circle of light persists. This circle contains the entire outside universe, compressed and distorted by the extreme curvature of space-time. Every star, every galaxy, every photon from the cosmic microwave background, all of it is funneled into this shrinking region of your visual field. The compression is not uniform. Stars that were scattered across the sky are now clustered together, their positions shifted by gravitational lensing. Light that was traveling in different directions outside the black hole has been bent onto similar paths by the gravity, converging into tighter and tighter bundles. The effect is a bit like looking through a wide-angle lens or a fisheye, but far more extreme. The universe is being wrapped around the geometry of the black hole, and you're seeing the result. As you fall deeper, the circle of light grows smaller. Not because the universe is shrinking, but because the angles at which light can reach you are becoming more restricted. The event horizon forces all light inward, and the deeper you go, the more tightly constrained the paths become. The circle compresses toward a point, though it never quite reaches it, not until the singularity. The light within that circle is also changing in character. Photons lose energy as they climb out of gravitational wells, a process called gravitational redshift. But photons falling into a gravitational well gain energy. The light from outside the black hole falling inward with you becomes blue-shifted. Wavelengths compress, frequencies increase, energy rises. Red light shifts toward blue, blue toward ultraviolet, ultraviolet toward X-rays. The process is gradual, but it's cumulative. The deeper you fall, the more blue-shifted the light becomes. In principle, this means that the universe behind you should appear brighter, more energetic than it did from outside. The cosmic microwave background, that faint glow of radiation left over from the Big Bang, normally in the microwave part of the spectrum, would shift into the infrared, then visible, then ultraviolet. Starlight would shift from visible into X-rays. The entire electromagnetic spectrum of the universe would slide toward higher energies. In practice, there are complications. The amount of light reaching you depends on how much is actually falling into the black hole at any given moment. And if the black hole is isolated, not actively feeding, that amount might be very small. The blue shift is real, but if there's not much light to begin with, the effect might not be overwhelming. Still, in theory, as you approach the singularity, the light from outside could become intensely energetic. A concentrated beam of high-energy radiation streaming in from the compressed circle of the universe. Ahead of you, in the direction of the singularity, there is still only darkness. No light escapes the singularity to illuminate the path ahead. No photons travel outward within the event horizon. Everything is moving inward, including light, and so the direction of your fall remains black, featureless, revealing nothing of what's to come. This creates an eerie asymmetry. Behind you, the universe is visible, bright, perhaps growing brighter. Ahead, nothing. You're falling through a tunnel of light and void, the past and the outside still present but receding, the future and the interior hidden entirely. The distortions you see are not just compressions and shifts of color, There are also warps in the apparent positions and shapes of objects. A star that should appear as a single point might be smeared into an arc, its light bent along multiple paths that reach your eyes from slightly different angles. Clusters of stars might appear duplicated, their images split by the extreme lensing. The geometry of spacetime is folding the visual information from the outside universe in complex ways, creating a view that has no analog in everyday experience. There's also the question of time. The light you're seeing was emitted from the outside universe at various moments in the past. And because of the way time dilation and light propagation work near the event horizon, you might be seeing light from a range of different times compressed into a single view. Events that occurred years apart outside might appear to happen simultaneously from your frame of reference. The universe's history is being collapsed, layered, presented in a single glance. This effect is subtle, hard to quantify without detailed calculations, but it adds to the strangeness. You're not just seeing the universe distorted in space, but also in time. The light carries information about what was happening out there when it was emitted, and the warping of space-time mixes those moments together. Some theoretical models suggest that in the final moments before you reach the singularity, you might see a flash, a burst of high-energy radiation as all the remaining light from outside, infinitely blue-shifted, converges on you in an instant. This flash would be brief, overwhelming, and possibly the last thing you'd perceive before tidal forces or the singularity itself ended the journey. But the models are uncertain. The extreme conditions near the singularity are beyond the regime where general relativity alone is reliable. Quantum effects, not included in classical models, might change the outcome. For now, though, you're still falling, still watching the universe compress behind you, still surrounded by the evidence of light's strange journey through curved spacetime. The view is hypnotic, constantly shifting, a visual representation of geometry and gravity made manifest. The darkness ahead is absolute. The light behind is all that remains of the outside world, and it's shrinking, blue shifting, intensifying. You're moving through a region where light itself is a prisoner, where every photon's path leads inward, where the geometry of the universe has closed in around you. And yet, the light still reaches you, still carries information, still connects you to the stars and galaxies beyond the event horizon. For as long as that connection lasts, the universe is still visible, still present, still watching from the outside, even as you descend into the interior. Gravity is not uniform. It's stronger closer to the source and weaker farther away. And this difference, this gradient, creates forces that can stretch and compress objects. These forces are called tidal forces, and they're the reason oceans rise and fall on Earth as the moon passes overhead. Near a black hole where gravity is immense and distances are small, tidal forces can become extreme. Imagine you're falling feet first toward the singularity. Your feet are closer to the center of the black hole than your head, and so they experience slightly stronger gravity. The difference is small when you're far from the black hole, but as you get closer, the gradient steepens and the difference grows. Your feet are pulled harder than your head, and your body begins to stretch, gently at first, then more insistently. At the same time, there's a horizontal component to the tidal force. Gravity pulls everything toward the center, and if your arms are spread out to the sides, they're being pulled not straight down, but slightly inward, toward the center line of your body. The effect is a compression from the sides and a stretching along the vertical axis. This combination of stretching and squeezing is what defines tidal forces. For a small black hole, a stellar mass black hole like the one you're falling into, the tidal forces become lethal long before you reach the event horizon. The gradient of gravity is steep, the differences between your head and feet significant even at a distance. By the time you're a few hundred kilometers from the horizon, the stretching force would exceed what your body can withstand. Bones would break, tissues would tear, and eventually you'd be pulled apart into a long, thin stream of atoms. This process is sometimes called spaghettification, a term that's both accurate and slightly absurd. The stretching would be gradual at first, uncomfortable but not immediately destructive. But gravity's gradient increases as you descend, and the forces grow exponentially. What begins as a gentle pull becomes an inexorable tearing. There would be no way to resist it, no way to hold yourself together. The tidal force is a consequence of the geometry of spacetime, not something you can shield against or counteract. It's simply a fact of being in a strong gravitational gradient. By the time you reach the event horizon, if you somehow survived, you'd be stretched into a thin filament, a column of matter, perhaps meters long, but only millimeters wide. And the stretching wouldn't stop there. Inside the event horizon, the gradient continues to steepen, the tidal forces continue to grow, and the process continues until, well before you reach the singularity, you've been torn down to individual atoms, then perhaps to subatomic particles, a stream of matter falling inward along a geodesic. This is the fate that awaits anything falling into a small black hole. Not a dramatic crushing, not an explosion, just a quiet, relentless stretching along the direction of gravity. It's a consequence of the curvature of spacetime, of the fact that gravity's strength changes with distance, and that change becomes extreme near a compact, massive object. But the experience would be very different if you were falling into a larger black hole. A supermassive black hole, the kind found at the centers of galaxies, can be millions or even billions of times the mass of the Sun. The event horizon of such a black hole is vast, millions or billions of kilometers in radius. And here's the key difference. The tidal forces at the event horizon depend not just on the mass of the black hole, but on the curvature of spacetime. And curvature decreases as the black hole gets larger. For a supermassive black hole, the event horizon is so far from the singularity that the curvature of spacetime at the horizon is relatively gentle. The gradient of gravity, the difference between your head and your feet, would be small, perhaps imperceptible. You could cross the event horizon of a supermassive black hole without feeling any significant tidal force. You'd be in free fall, weightless, comfortable. You might not even realize you'd crossed. This is one of the strange features of black holes. The event horizon is a point of no return, an absolute boundary. But it's not necessarily a place of violence. For a large enough black hole, crossing the horizon is uneventful. You simply pass through an invisible surface, and your fate is sealed, but you feel nothing unusual. The tidal forces that will eventually destroy you are present, but they're not yet strong. They grow as you fall deeper toward the singularity, but at the horizon, they're mild. Inside a supermassive black hole, you could survive for a significant amount of time. Minutes, perhaps hours, depending on the mass and your trajectory. You'd continue to fall weightless, watching the universe compress behind you, experiencing time normally. The tidal forces would increase gradually, imperceptibly at first, then more noticeably. At some point, you'd begin to feel the stretching, the discomfort, the realization that the force was growing and that there was nothing you could do to stop it. Eventually, even in a supermassive black hole, the tidal forces would become lethal. The singularity is a region of infinite curvature, and as you approach it, the gradient of gravity becomes infinite as well. No matter how large the black hole, no matter how gentle the crossing of the event horizon, the end is the same. Tidal forces grow without bound, and you're stretched, compressed, torn apart at the atomic level. But the journey to that end would be very different. In a small black hole, death comes quickly, before you even cross the horizon. In a large black hole, you have time, a strange grace period inside the event horizon where you're doomed but not yet destroyed. You can look around, observe, think. You're inside the most extreme object in the universe, and you're still conscious, still experiencing. There's a particular mass where the tidal force at the event horizon is just barely tolerable, where a human might cross and survive for a few moments before the forces deeper inside become overwhelming. The exact mass depends on assumptions about human tolerance, about how much stretching a body can endure, but it's somewhere in the range of thousands to tens of thousands of solar masses. Smaller than a supermassive black hole, much larger than a stellar one. A black hole in this range would be rare, but they may exist, intermediate mass black holes that have been detected in some star clusters. Falling into such a black hole would be the ultimate edge case, a journey where you could cross the point of no return intact, aware, and survive just long enough to experience the interior before the inevitable end. It's a thought experiment more than a realistic scenario, but it highlights the diversity of black holes, the way their size changes not just their mass, but the very experience of approaching them. Tidal forces are invisible from a distance, encoded in the geometry of space-time, but they're one of the most tangible consequences of falling into a black hole. They're what transforms an abstract concept, curvature, geodesics, singularities, into something physical, something that affects matter and bodies and structure. They're the reason a black hole doesn't just trap you, but disassembles you, breaks you down into the most basic components, until what remains is not you but a stream of particles, indistinguishable from any other matter falling into the unknown. Black holes come in different sizes, and size matters in ways that aren't immediately obvious. A black hole's mass determines not just how strong its gravity is, but how large its event horizon is, and how steeply space-time curves at that horizon. These differences change the experience of falling in, the time you'd survive, and the intensity of what you'd encounter. A stellar mass black hole, formed from the collapse of a massive star, typically has a mass between about 3 and 20 times the mass of the Sun. The event horizon is small, on the order of 10 to 60 kilometers in radius. Space-time near the horizon is sharply curved. Gravity's gradient is steep, and tidal forces become lethal well before you reach the boundary. If you were falling into such a black hole, you'd be torn apart while still outside, still technically in a region where escape is possible if you had enough thrust. But you wouldn't escape. The forces would destroy you first. The singularity at the center is close, just tens of kilometers from the event horizon. Once you cross, if somehow you crossed intact, The journey to the singularity would take a fraction of a second. There would be no time to observe, no time to think. The fall from horizon to singularity is brief, a quick descent into a region where space-time curvature becomes infinite and all known physics breaks down. A supermassive black hole is a different kind of object. These black holes reside at the centers of galaxies, and they can be millions, billions, even tens of billions of times the mass of the Sun. The one at the center of our galaxy, Sagittarius A star, is about 4 million solar masses. The one at the center of the galaxy, M87, famously imaged by the Event Horizon Telescope, is about 6.5 billion solar masses. These are not just larger versions of stellar mass black holes. They're fundamentally different environments. The event horizon of a supermassive black hole can be millions of kilometers across, larger than the orbit of Earth around the Sun. For the M87 black hole, the event horizon has a radius of about 20 billion kilometers, roughly 4 times the distance from the Sun to Neptune. The size is almost incomprehensible. You could fit the entire solar system out to the orbit of Pluto inside the event horizon with room to spare. Because the horizon is so far from the singularity, the curvature of space-time at the horizon is gentle. The tidal forces are weak, far weaker than the tidal forces you'd experience standing on Earth, due to the moon's gravity. You could cross the event horizon of a supermassive black hole and feel nothing unusual. You'd be in free fall, weightless, as you have been all along. The boundary would pass around you invisibly, and you'd continue inward, still intact, still conscious. The journey from the event horizon to the singularity in a supermassive black hole can take hours. During that time, you'd fall through a vast, empty region where space-time is curved, but not catastrophically so. The tidal forces would grow, slowly, imperceptibly at first. You'd have time to observe, to think, to process what's happening. It's a strange kind of grace, a long, quiet descent into the ultimate unknown. Of course, the end is the same. The singularity is still there, still a region of infinite curvature, still a place where tidal forces grow without bound. No matter how large the black hole, no matter how gentle the crossing, the singularity will eventually tear you apart. But the experience leading up to that moment is vastly different depending on the black hole's mass. There are also intermediate mass black holes, objects between stellar mass and supermassive. Though these are less well understood, they'd have masses in the hundreds or thousands of solar masses, event horizons somewhere between the extremes. The experience of falling into one would be intermediate as well. Tidal forces at the horizon might be strong, but not immediately lethal. The journey inside might last seconds or minutes, rather than fractions of a second or hours. The mass of a black hole also affects how it interacts with its surroundings. Stellar mass black holes are often found in binary systems, orbiting another star, sometimes pulling material from that star, and forming bright accretion disks. Supermassive black holes sit at the centers of galaxies, surrounded by millions or billions of stars, often fed by gas and dust from the galaxy itself. The environments are different, and if you were falling into a black hole in reality, the things around it, accretion disks, jets, nearby stars, would affect what you see and experience. An isolated black hole, far from any star or gas, would be dark, silent, visible only by its gravitational effects. A black hole with an accretion disk would be surrounded by a bright, swirling structure of matter heated to millions of degrees, emitting intense radiation across the spectrum. The disk would be visible as you approach, a glowing ring around the black hole's silhouette. If you fell through the disk, you'd be bombarded by radiation and particles, lethal long before tidal forces became an issue. For the purposes of this journey, we've been imagining an isolated black hole, quiet and dark, so that the experience is shaped only by gravity and geometry, not by external hazards. But in reality, most black holes are not isolated. They're embedded in environments, surrounded by matter and energy, and those surroundings would change the journey significantly. Still, the fundamental difference between stellar mass and supermassive black holes remains. One kills you quickly before you even cross the threshold, while the other allows you to cross and survive, at least for a time, experiencing the interior as a place you can inhabit, however briefly. It's a consequence of scale, of the way gravity's strength and curvature relate to distance, and it's one of the many ways black holes challenge our intuitions about space and time and survival. Most black holes rotate. In fact, it's likely that all black holes rotate to some degree because they form from the collapse of rotating stars, and angular momentum is conserved during collapse. When a star's core collapses down to a few kilometers in radius, its rotation speed increases enormously, like a figure skater pulling in their arms. The resulting black hole spins, sometimes at extraordinary rates, and this rotation changes the structure of space-time around it. A rotating black hole is called a Kerr black hole, named after the physicist Roy Kerr, who first described its geometry mathematically. It's more complex than a non-rotating Schwarzschild black hole, with additional features and regions that don't exist in the simpler case. The most striking of these is the ergosphere. The ergosphere is a region outside the event horizon where space-time itself is dragged around by the black hole's rotation. Inside the ergosphere, it's impossible to remain stationary. No matter how powerful your rockets, no matter how much thrust you apply, you cannot stop the rotation. You're forced to move in the direction of the black hole's spin, carried along by the rotating space-time itself. You can still escape from the ergosphere. You're still outside the event horizon, but you cannot stand still. The boundary of the ergosphere is called the outer surface, or sometimes the static limit. It's shaped like a flattened sphere bulging at the equator and touching the event horizon at the poles. Inside this boundary, space is moving, rotating with the black hole. The effect is strongest near the equator, where the black hole's rotation is fastest and weakest at the poles. If you're falling into a rotating black hole, your trajectory begins to curve as you enter the ergosphere. You're still falling inward, still being pulled by gravity, but now you're also being swept around, forced to orbit. The combination of inward fall and rotational dragging creates a spiral, a corkscrew path that takes you around the black hole as you descend. The tighter the spiral, the faster the black hole is rotating. The event horizon of a rotating black hole is also different. It's not a perfect sphere. It's an oblate spheroid, flattened at the poles, bulging slightly at the equator. The radius of the horizon depends on the black hole's spin. A maximally rotating black hole has a smaller event horizon than a non-rotating black hole of the same mass. The rotation, in a sense, holds the horizon closer to the singularity. Inside the event horizon of a rotating black hole, there's another structure called the inner horizon, or Cauchy horizon. This is a second boundary, deeper inside, beyond which the predictability of general relativity starts to break down. Theoretical models suggest that the inner horizon is unstable, that any small perturbation, any infalling matter or light, could cause it to become a region of infinite energy density, a kind of secondary singularity. The physics here is speculative, uncertain, and likely requires quantum gravity to fully understand. The singularity itself, in a rotating black hole, is not a point but a ring. It's a circle of infinite density, lying in the equatorial plane of the black hole. In principle, you could pass through the center of the ring without hitting the singularity, though what would happen if you did is unknown. Some solutions to the equations of general relativity suggest that passing through the ring could take you to another region of spacetime, possibly another universe, or a different part of our own universe. These solutions are mathematically valid, but probably not physically realistic. Small perturbations, quantum effects, or instabilities would likely destroy the structure before you could pass through. Still, the idea is fascinating. A rotating black hole, at least in the idealized mathematics, contains not just a point of destruction, but a kind of gateway, a ring through which, in theory, something might pass. Whether this is real, whether it survives the inclusion of quantum mechanics, whether it has any physical meaning at all, remains unknown. The rotation of a black hole also affects the light and distortions you'd see as you approach. The dragging of space-time pulls light along with it, creating asymmetries in the visual field. Light emitted in the direction of rotation is carried along faster, while light emitted against the rotation is slowed. This creates a kind of Doppler effect, where one side of the black hole appears brighter and the other dimmer. One blue shifted and the other red shifted, even if the source of light is symmetric. If you're spiraling inward, caught in the ergosphere, the view would rotate as well. The stars, the outside universe, would appear to circle around you, not because you're spinning, but because space-time itself is spinning, and you're being carried with it. The effect would be disorienting. A constant slow rotation overlaid on the already strange distortions of gravitational lensing. The energy in a black hole's rotation is enormous. In principle, it's possible to extract energy from the ergosphere, a process called the Penrose process. If you drop an object into the ergosphere and then split it, sending one piece into the black hole and the other back out, the piece that escapes can carry more energy than the original object had. The extra energy comes from the black hole's rotation, which decreases slightly in the process. This is speculative technology, the stuff of distant civilizations, but it's allowed by the laws of physics as we understand them. For you, falling inward, the rotation is just another layer of complexity, another way the black hole shapes space-time, and your journey through it. You spiral as you fall, the universe rotates around you, and the darkness ahead remains, waiting, concealing the ring's singularity and whatever lies beyond the mathematics. Crossing the event horizon changes everything, but in ways that are not immediately obvious. From your perspective, the moment of crossing is smooth, unmarked by any physical sensation or visual cue. But something fundamental has shifted in the geometry of space-time. You are now in a region where every possible future, every path you could take, leads inward toward the singularity. Escape is not difficult or unlikely. It's impossible, ruled out by the structure of space-time itself. This is often described by saying that time and space swap roles inside the event horizon. Outside, you can move freely in space, forward, backward, left, right, but you're compelled to move forward in time. Inside, the reverse is true in a sense. The radial direction, the direction toward the singularity, becomes time-like. You cannot move backward radially any more than you can move backward in time outside the black hole. The singularity is not a place ahead of you. It's a moment in your future, as inevitable as tomorrow. This is abstract, difficult to grasp, and the mathematics behind it requires general relativity's full machinery. But the consequence is clear. You cannot stop, cannot turn around, cannot avoid what's coming. The geometry gives you no choice. All geodesics, all paths through space-time, converge on the singularity. You're following one of those paths, and it has only one destination. The time remaining until you reach the singularity depends on the black hole's mass and your current position. For a stellar mass black hole, the journey from event horizon to singularity is brief, measured in fractions of a second. For a supermassive black hole, it could be minutes or hours. During that time, you're in a region of space that, in a real sense, exists outside the rest of the universe. No signal you send can escape. No light from inside can reach the outside. You are isolated, cut off, in a pocket of space-time that is causally disconnected from everything beyond the horizon. The view continues to change as you fall. The circle of light behind you, the compressed image of the outside universe, continues to shrink. The stars are brighter now, blue shifted as the light gains energy falling into the gravitational well. The entire electromagnetic spectrum shifts upward. Microwave background radiation becomes visible light. Starlight becomes ultraviolet. Then X-rays. If there's enough light falling in with you, the view might become intensely bright, a blazing ring of high-energy radiation. Ahead, the darkness persists. No light comes from the singularity. No glow, no indication of what's there. The singularity is still in your future, still hidden by the geometry of time and space. You're falling through a void, guided only by the pull of gravity and the shape of space-time. Tidal forces are increasing. If you're in a supermassive black hole, they're still mild, a gentle stretching that you might not notice yet. But they're growing steadily as the gradient of gravity steepens with each moment of your descent. Your feet are being pulled harder than your head. Your body is being stretched vertically and compressed horizontally. The forces are subtle at first, then uncomfortable, then painful, then unbearable. At some point, the tidal forces exceed what your body can withstand. Bones crack, tissues tear. The structure that holds you together fails. You're pulled apart, not explosively, but gradually, stretched into a long, thin stream of matter. Consciousness would end long before the process completes. Perhaps when the brain is deprived of blood. Perhaps when the forces disrupt neural function. But the matter that was you continues to fall, continues to stretch, continues inward. Eventually, even atoms cannot hold together under the tidal stress. Electrons are stripped from nuclei. Nuclei are pulled apart into individual protons and neutrons. And perhaps, closer still to the singularity, even those particles break down into quarks. The structure of matter, built from forces and fields and quantum rules, is overwhelmed by the curvature of space-time. What remains is a stream of fundamental particles, indistinguishable from any other infalling matter, descending toward the singularity. The singularity itself is a point, or in the case of a rotating black hole, a ring, where space-time curvature becomes infinite. General relativity predicts that density, temperature, tidal forces, all physical quantities become infinite there. But this prediction is almost certainly wrong. General relativity is a classical theory, and it breaks down at sufficiently small scales or high energies. Quantum mechanics, which governs the behavior of particles and fields, must play a role, but we don't yet have a complete theory of quantum gravity that describes what actually happens at the singularity. It's possible that the singularity is not a point of infinite density, but a region of extremely high but finite density, smoothed out by quantum effects. It's possible that space-time itself becomes discrete, granular at the smallest scales, and the singularity is replaced by some kind of quantum structure. It's possible that the singularity is a boundary beyond which space-time simply doesn't exist, or exists in a form we don't yet understand. What's clear is that the singularity represents the limit of our current knowledge. General relativity predicts its existence, but also predicts its own failure there. The equations produce infinities, a signal that the theory is incomplete. To know what actually happens at the center of a black hole, we'd need a theory that unifies general relativity and quantum mechanics. And despite decades of effort, we don't have one yet. For you, falling inward, the singularity is the end of the journey. Whether it's a point of infinite density, a quantum structure, or something else entirely, it's a place where your path through space-time terminates. The mathematics offers no continuation, no path beyond. Time, at least as we understand it, ends there. But there's a strange sense in which the singularity is not part of the black hole's interior. It's a boundary, an edge of space-time, rather than a place within it. Some descriptions treat it as a moment in time, the final moment, rather than a location in space. The distinction is subtle, and perhaps more philosophical than physical, but it underscores how strange the geometry becomes near the center. Inside the event horizon, you're in a region that general relativity describes but cannot fully explain. The equations work, the predictions are consistent, but they point toward a breakdown, a place where the theory admits its own limits. You're falling through that region, experiencing the consequences of extreme curvature, moving toward a boundary that represents the edge of known physics. The journey is brief, silent, and irreversible. The universe outside continues. Stars burn, galaxies evolve, but for you, time is running out, converging on a singular moment where all paths end. Black holes are not entirely black. In 1974, Stephen Hawking showed that when you account for quantum mechanics, black holes emit radiation, a faint glow of particles created near the event horizon. This radiation, now called Hawking radiation, arises from quantum fluctuations in the vacuum of space, and it causes black holes to slowly lose mass over time, a process known as evaporation. The mechanism is subtle. In quantum field theory, empty space is not truly empty. Particle-antiparticle pairs are constantly appearing and disappearing, flickering in and out of existence over timescales so short that they don't violate the conservation of energy. Near the event horizon of a black hole, one member of such a pair can fall into the black hole while the other escapes. To an outside observer, it appears as though the black hole is emitting particles. The energy for these particles comes from the black hole's mass, which decreases very slightly with each emitted particle. For a stellar mass black hole, the rate of Hawking radiation is extraordinarily slow. The black hole emits particles at a temperature far colder than the cosmic microwave background, so it actually absorbs more energy from the universe than it radiates. It's growing, not shrinking. But for a very small black hole, the temperature is higher and the evaporation is faster. A black hole with the mass of a mountain would evaporate in a fraction of a second, releasing enormous energy in the process. For a supermassive black hole, the evaporation time is inconceivably long, far longer than the current age of the universe. These black holes will persist for 10 to the 100 years or more, slowly radiating away their mass over timescales that dwarf anything we can easily imagine. But eventually, in the unimaginably distant future, they will evaporate completely, leaving behind only radiation and perhaps some quantum remnant. This raises a profound problem known as the black hole information paradox. In quantum mechanics, information is never truly lost. The state of a system at one time uniquely determines its state at any future time. And in principle, you could reverse the evolution and recover the initial state. But if a black hole evaporates completely, what happens to the information about everything that fell in? All the details about the particles, their quantum states, the arrangement of matter, everything that defined the infalling objects. Where does it go? If the information is lost, destroyed at the singularity, or erased by evaporation, then quantum mechanics is violated. If the information is somehow preserved, encoded in the Hawking radiation, or stored in the black hole structure, then we need a mechanism to explain how. The paradox has been debated for decades, and it touches on some of the deepest questions in theoretical physics. One proposed solution is that information is encoded in the Hawking radiation itself, scrambled and distributed across the particles in ways we don't yet understand how to decode. The information isn't lost, just transformed into a form so complex that retrieving it would require analyzing every particle of radiation emitted over the black hole's entire lifetime. This preserves quantum mechanics, but leaves open the question of how exactly the encoding happens, especially since Hawking radiation appears to be thermal, random, carrying no obvious trace of what fell in. Another idea involves what's called the holographic principle. This suggests that all the information about the three-dimensional interior of a black hole is somehow encoded on the two-dimensional surface of the event horizon, much like a hologram encodes a three-dimensional image on a flat surface. If this is true, then the event horizon is not just a boundary, but a repository of information. And the radiation emitted as the black hole evaporates carries away that information bit by bit. The holographic principle has gained support from string theory and other approaches to quantum gravity, but a complete mathematical description of how it works for black holes remains elusive. A more dramatic proposal is the firewall hypothesis. This suggests that the event horizon might not be empty space at all, but a wall of high-energy particles that would incinerate anything attempting to cross. The firewall would arise from quantum entanglement conflicts between particles inside and outside the horizon, a consequence of trying to preserve information while maintaining the predictions of general relativity. If firewalls exist, your experience falling into a black hole would be very different from the smooth crossing predicted by classical physics. You would be destroyed at the horizon, not deep inside. But this idea conflicts with the equivalence principle, a cornerstone of general relativity that says falling freely through space should feel the same anywhere, with no special markers at the event horizon. The firewall paradox remains unresolved. It's worth noting that none of these quantum effects would be noticeable during your fall. Hawking radiation is far too faint to see or feel. If a firewall exists, it would act on scales so small and with energies so extreme that it's unclear whether it would manifest as a physical barrier or remain a quantum phenomenon invisible to classical observers.
The information paradox is a theoretical problem, not an experiential one.
From your perspective, falling in, the journey would likely proceed just as general relativity predicts, smooth and inevitable, until tidal forces or the singularity intervene. But the existence of these questions tells us something important. Black holes are places where our two great theories of physics, general relativity and quantum mechanics, come into direct conflict. General relativity governs gravity, space-time, and the large-scale structure of the universe. Quantum mechanics governs particles, fields, and the behavior of matter and energy at the smallest scales. Both theories are extraordinarily successful within their own domains, but they are fundamentally incompatible. General relativity is deterministic and smooth. Quantum mechanics is probabilistic and grainy. At the event horizon, and especially at the singularity, both theories are needed, but we don't yet have a unified theory that combines them. This missing theory is often called quantum gravity. It would describe how space-time itself behaves at the smallest scales, how gravity emerges from quantum processes, and what happens in regions of extreme density and curvature, like black hole singularities and the early universe. String theory, loop quantum gravity, and other approaches attempt to construct this theory, and they've made progress, but none has been confirmed experimentally. Black holes are one of the few places in the universe where quantum gravity effects might be strong enough to matter, which makes them natural laboratories for testing ideas, even if we can't visit them directly. The information paradox is a symptom of this larger puzzle. It arises because we're trying to apply quantum mechanics, which requires information preservation, to black holes, which are described by general relativity, a theory that allows information to disappear behind horizons and into singularities. The paradox won't be fully resolved until we have a complete theory of quantum gravity that can describe the entire life cycle of a black hole, from formation to evaporation, in a way that respects both quantum mechanics and general relativity. What this means for your fall is uncertain. If information is preserved in subtle quantum correlations across the event horizon, your journey inward might be conventional, just as general relativity predicts, with quantum details too fine to notice. If firewalls exist, your experience at the horizon might be catastrophic in ways classical physics doesn't predict. If the singularity is smoothed out by quantum effects into some kind of exotic structure, your final moments might be strange in ways we can't yet imagine. We don't know because we don't have the physics to answer the question. And that's where the mystery rests, not in drama or danger, but in the quiet acknowledgement that black holes touch the edges of what we understand. They exist, we observe them, we measure their masses and spins, we detect them merging and emitting gravitational waves. But their interiors, their quantum behavior, the fate of information and matter that crosses the horizon, all of that remains beyond our current grasp. falling into a black hole would take you past the boundaries of known physics, into a realm where our equations break down and our intuitions fail. It's a journey not just through space, but to the limits of human knowledge itself. General relativity predicts singularities, points of infinite density, where space-time curvature becomes unbounded and the equations cease to give meaningful answers. But infinity in physics is often a sign that a theory has reached its limits. Many physicists suspect that singularities don't actually exist in nature, that they're artifacts of applying general relativity beyond its valid range. If quantum gravity smooths out the singularity, replaces it with something else, then the interior of a black hole might be very different from what classical theory predicts. One possibility is that quantum effects, strong only at extraordinarily small scales, halt the collapse before a singularity forms. Instead of crushing down to a point of infinite density, matter might compress to some minimum size set by quantum mechanics, forming a dense but finite core. This core could be stable, held up by quantum pressure that has no classical analog, or it could be dynamic, bouncing or oscillating in ways we can't yet describe. If this is the case, the singularity would be replaced by a region of extreme but finite curvature, still far beyond anything we can probe experimentally, but not infinite, not a breakdown of physics. Some models suggest that this quantum core could undergo a process called a quantum bounce. As matter collapses inward, it compresses to near-Planck densities, the scale where quantum gravity effects dominate, and then rebounds, expanding outward again. The energy from the collapse could drive an explosion, but the event horizon would trap this explosion inside, at least temporarily. The interior might form a temporary universe of its own, expanding and possibly recollapsing, invisible to the outside. These are sometimes called Planck stars, speculative objects that exist at the boundary between black holes and quantum foam. Whether they can actually form, and what signals they might produce if they do, remains an open question. Another idea comes from string theory, a framework where particles are not points, but tiny vibrating strings. In string theory, black holes might not have a traditional event horizon and singularity at all. Instead, they could be fuzzballs, tangled masses of strings and higher dimensional structures that occupy the entire region where we expect the event horizon to be. From a distance, a fuzzball would look like a black hole, with similar gravitational effects, but up close, it would be something entirely different. A dense, stringy structure with no interior, no singularity, and no information paradox, because all the information is encoded in the arrangement of the strings. The idea is mathematically appealing, but it requires string theory to be correct, and string theory has not yet been confirmed by observation. There's also the speculative notion of gravastars, short for gravitational vacuum stars. In this model, the collapsing matter doesn't form a singularity or even reach the center. Instead, quantum vacuum energy, the energy associated with empty space itself, becomes important near the would-be singularity and halts the collapse. The result is a thin shell of matter surrounding a core of exotic vacuum energy. With negative pressure, the event horizon, if it forms at all, would be a razor-thin boundary at the shell's surface. Gravastars are purely theoretical, with no observational evidence supporting them. But they represent an attempt to avoid singularities without invoking exotic quantum gravity effects. Then there are wormholes, solutions to the equations of general relativity, where space-time is curved in such a way that two distant regions are connected by a tunnel. Some rotating black hole solutions mathematically contain wormholes, pathways through the singularity to another region of space-time, or even another universe entirely. If you fell into a rotating black hole and somehow survived the journey to the ring singularity, you might, in principle, pass through it and emerge elsewhere. But the mathematics that allow this are fragile. Wormholes, if they exist, are likely unstable, collapsing before anything could traverse them, or they require exotic matter with negative energy to hold them open, matter we've never observed and may not exist. The idea is fascinating, but there's no evidence that black holes actually contain traversable wormholes, and most physicists consider them unlikely. What all these alternatives share is an attempt to replace the singularity with something less pathological, something that doesn't involve infinite density or the breakdown of physics. They reflect a discomfort with infinities, a sense that nature should be more elegant, more comprehensible than general relativity's stark prediction of collapse to a point. But discomfort is not evidence, and elegance is not proof. The universe is under no obligation to conform to our preferences. For someone falling into a black hole, the question of which model, if any, is correct would matter enormously in the final moments. If singularities are real, you encounter one, though the meaning of that encounter is unclear. If quantum bounces occur, you might be part of a chaotic, rebounding collapse deep inside the horizon. If the interior is a fuzzball, you wouldn't reach a singularity at all, just dissolve into the stringy structure. If a wormhole exists, and if conditions are right, you might pass through, though to where and in what state is anyone's guess. Each scenario is radically different, and we have no way yet to determine which, if any, is realized in nature. What we do know is that these questions can't be answered with current physics. General relativity alone can't tell us what happens at the singularity, because it predicts its own breakdown there. Quantum mechanics alone can't describe black holes, because it doesn't include gravity in a fundamental way. The answer lies somewhere in the synthesis, in a theory of quantum gravity that doesn't yet exist in complete form. Until we have that theory, and until we find ways to test it, the interior of a black hole remains a realm of speculation, of models and mathematics that gesture toward possibilities without confirming them. None of this changes what we observe from outside. Black holes exist, their horizons are well defined. Their effects on space-time and surrounding matter are measurable and consistent with general relativity. The uncertainty is not about whether black holes are real, but about what happens in regions we can't observe, under conditions we can't replicate, governed by physics we don't yet fully understand. It's a profound and humbling reminder that the universe contains spaces our knowledge cannot yet reach. If you were falling into a black hole, your experience would be one thing, but to someone watching from a safe distance, far from the event horizon, the story would be entirely different. From their perspective, you would never actually cross the horizon at all. As you descend closer to the event horizon, time dilation becomes more and more extreme. Clocks near the horizon run slower compared to clocks far away, an effect predicted by general relativity and confirmed in many contexts. For you, falling freely, time flows normally. Your watch ticks at the usual rate, your thoughts proceed at their usual pace. But to the distant observer watching through a telescope, your movements begin to slow. You fall more and more slowly as you approach the horizon, as if moving through an increasingly thick fluid, though you feel nothing of the sort. The effect intensifies the closer you get. At some distance from the horizon, you appear to the observer to take minutes to fall a kilometer. Closer still, hours to fall a meter. Closer again, years to fall a centimeter. The observer never sees you reach the horizon itself. You approach it asymptotically, your motions slowing without limit, frozen in an eternal fall that never quite completes. At the same time, the light coming from you becomes redshifted. As photons climb out of the deepening gravitational well to reach the distant observer, they lose energy, their wavelength stretches, their color shifts toward the red end of the spectrum and beyond. If you were shining a blue light as you fell, the observer would see it turn green, then yellow, then red, then infrared, then into radio wavelengths, dimming all the while. Eventually, the light becomes so redshifted and faint that the observer can no longer detect it. You fade from view, a dimming, reddening echo that stretches out in time, but never disappears entirely. At least not in any finite time the observer experiences. From the observer's perspective, you are forever approaching the horizon, never crossing, gradually fading into the background glow of the universe. If they could watch for an infinite amount of time, with perfect instruments, they would see you inch closer and closer to the horizon, but never pass it. The crossing, from their point of view, is postponed indefinitely, pushed infinitely far into the future. This is not an illusion or a trick of perception. It's a consequence of how space-time is curved near a black hole, and how time is relative. The distant observer and you, the infalling traveler, are experiencing time differently. What takes a finite, brief time for you, the crossing of the horizon, is stretched into an infinite duration for them. Both perspectives are equally valid. Both describe the same event, but they are irreconcilable in a simple, intuitive way. The crossing happens and doesn't happen, depending on who's watching and where they are. From your perspective, falling inward, the universe above changes as well. Light from the outside continues to reach you even after you cross the horizon, though it appears increasingly compressed and blue-shifted. Because you are falling into a region of increasingly warped space-time, you see time outside the black hole appear to speed up. Stars might seem to age more quickly, their light cycling through lifetimes in moments from your point of view. If you fell into a supermassive black hole and survived long enough inside the horizon, looking back, you might see the universe beyond age by millions or even billions of years in the brief time before tidal forces or the singularity end your journey. This creates a strange asymmetry. The outside universe sees you freeze and fade. You see the outside universe accelerate and brighten. Two observers watching each other would see radically different timelines unfold. Neither is wrong. Time near a black hole is not a single universal flow, but a patchwork of perspectives, each valid within its own frame of reference, each incompatible with the others in straightforward terms. What does this mean for the concept of now? If the distant observer never sees you cross, does the crossing happen in their present, their future, or not at all? If you cross quickly and continue inward, experiencing the interior, Does that interior exist for the distant observer? Or is it a region of space-time they can never confirm exists? These questions don't have simple answers within general relativity. The theory describes the geometry of space-time, how curves and clocks behave, but it doesn't privilege one observer's experience over another. Both are real, both are part of the same space-time, but they slice through it differently, experiencing different sequences of events. This observer-dependent nature of black hole crossings has implications for the information paradox as well. If the distant observer never sees you cross, never sees information past the horizon, then from their perspective, information never enters the black hole. It accumulates at the horizon, redshifted and time-dilated into an ever-thinner shell of radiation that slowly evaporates away as Hawking radiation. Perhaps, from that viewpoint, information is never lost because it never truly went inside. But from your viewpoint, you crossed, the information went with you, and the paradox remains. Reconciling these perspectives requires quantum gravity, and again, we don't yet have a complete framework for that. The distant observer also can't see what happens to you after crossing. They can't observe the interior, can't measure the singularity, can't test whether firewalls or fuzzballs or quantum bounces occur. The event horizon is not just a point of no return for matter and light, but a boundary of observability. Everything beyond it is hidden, not just practically, but fundamentally. No signal from inside can reach outside. The interior is causally disconnected from the external universe. This makes black holes unique among objects in the universe. Most things, even if distant or faint, can in principle be observed given enough time and sensitive instruments. But a black hole's interior is shielded, absolutely. The event horizon is a one-way membrane. Information flows in, but never out, except perhaps in the deeply scrambled form of Hawking radiation over cosmological timescales. What happens inside is forever beyond the reach of outside observers. You, falling in, would know, at least briefly. But you could never communicate that knowledge back. The light carrying your observations, your measurements, your final thoughts would be trapped inside, falling inward just as you are, unable to climb back out of the gravitational well. In a sense, the interior of a black hole is the most private place in the universe, witnessed only by those who can never share what they witnessed. The asymmetry between perspectives, between inside and outside, is one of the deep and strange features of black holes. It reminds us that time and space are not absolute, that observation and experience are woven into the fabric of reality in ways that can't be separated cleanly. What you see depends on where you are, and near a black hole, where you are determines not just what you see, but when and whether events occur at all. For all that we have learned about black holes, from their formation in collapsing stars to their detection through gravitational waves, much of what happens inside them remains unknown. The singularity, the event horizon's quantum structure, the fate of information, the details of the final moments of a fall, all of these are still beyond our grasp, waiting for theories we haven't yet completed and observations we can't yet make. We don't know what actually exists at the singularity. General relativity predicts infinite density and curvature, a point where space-time itself breaks down. But infinity is often a signal that a theory has overreached, that new physics is needed. Quantum gravity, whatever its final form, should replace the singularity with something finite, something comprehensible, but we don't yet know what that something is. A Planck scale core, a quantum bounce, a fuzzball, a wormhole throat, or something entirely unanticipated. The possibilities are many. The evidence is absent. We don't know whether firewalls exist. The firewall paradox arises from trying to preserve quantum information while respecting the equivalence principle. And different physicists favor different resolutions. Some argue firewalls are real, a violent quantum structure at the horizon. Others argue they're an artifact of incorrect assumptions, that information is preserved in subtler ways that don't require a firewall. Still others suggest the paradox signals a deeper misunderstanding of how quantum mechanics and gravity fit together. The debate continues unresolved. We don't know how information escapes, or if it does. The information paradox has prompted decades of research. And while progress has been made, particularly through holographic ideas and insights from string theory, a complete, universally accepted solution does not yet exist. How does the information encoded in matter and radiation that falls into a black hole get transferred to Hawking radiation? Is it encoded in correlations too subtle to detect? Is it preserved in the structure of space-time itself? Or is the paradox telling us that our understanding of quantum mechanics or space-time needs revision? We don't know what you would see in the final moments. Would the darkness ahead remain absolute? Or would quantum effects near the singularity create light, radiation, or structure visible in the last instance? Would tidal forces render you unconscious before anything unusual could be perceived? Or would the journey inside a supermassive black hole allow minutes of awareness in an environment no human has ever imagined? The question is experiential and unreachable, but it lingers. We don't know how many black holes contain wormholes, or if any do. The mathematics of rotating black holes allows for wormhole solutions, tunnels through space-time to other regions or other universes, but the physical realizability of these solutions is uncertain. Wormholes may collapse too quickly to traverse, or require conditions that never occur in nature, or simply not exist at all. Observations tell us nothing about this, because any signals from a wormhole's far end, if it has one, cannot reach us. We don't know whether black holes leave remnants when they evaporate. If Hawking radiation continues until the black hole's mass is nearly zero, what happens at the end? Does the black hole vanish completely, leaving only radiation? Or does it leave behind a stable remnant, a tiny, dense object that can't evaporate further? Remnants would avoid some aspects of the information paradox, but they raise other questions about how much information such a small object could store. We have theories, but no observations. We don't know how quantum gravity will change the picture. String theory, loop quantum gravity, and other approaches suggest modifications to the event horizon, the interior, and the singularity, but none of these theories are complete or confirmed. When we do have a working theory of quantum gravity, it may reveal that black holes are quite different from what general relativity alone predicts. Or it may confirm the classical picture in most respects, adding only small corrections. Until the theory exists and is tested, we can't say. We don't know if the equivalence principle holds exactly at the horizon. The principle states that freefall should feel the same everywhere, that there's nothing locally special about crossing an event horizon. Classical general relativity supports this, but quantum effects might introduce subtle or dramatic violations. Firewalls would be a dramatic violation. More subtle effects, like quantum entanglement across the horizon, might alter the experience in ways we can't yet predict. The question touches the foundations of how we understand gravity. We don't know whether black holes connect to other universes, whether they seed new space-time regions, whether the interiors are somehow larger or more complex than the exteriors suggest. These are speculative ideas, often untestable with current methods, but they reflect the openness of the question. Black holes sit at boundaries, not just of space, but of knowledge, and boundaries often hide surprises. All of these unknowns arise because black holes bring together gravity and quantum mechanics. The large and the small, the smooth and the grainy, in ways that our current physics can't fully describe. General relativity works beautifully for describing space-time outside the horizon, and quantum mechanics works beautifully for describing particles and fields in flat space-time. But inside a black hole, both are needed together, and we don't yet have a consistent framework for that. This isn't a failure, it's the frontier. Science advances by finding the places where current theories break down, where predictions fail or paradoxes arise, and then building new theories that resolve those issues. Black holes are one of those places. They've already taught us about space-time, gravity, and the limits of classical physics. They will likely teach us much more as we develop better theories and better tools to study them. What this means is that falling into a black hole would be a journey not just into extreme gravity, but into the unknown. You would pass through the event horizon, a boundary our best theories describe, but beyond which our certainty fades. You would move toward a singularity that may not exist as predicted. Through an interior that may be far stranger than a simple inward fall. You would experience time, light, and space in ways no current theory fully captures. And you would do so alone, unable to send back what you learned, unable to add your observations to the body of human knowledge. In a way, that's fitting. Black holes are places where information goes in and doesn't come out, where the universe hides its deepest secrets behind an impenetrable veil. They exist at the intersection of the known and the unknown, the observed and the unobservable. They remind us that the universe is larger and stranger than our current understanding, that there are regions of reality we can describe mathematically but cannot visit, phenomena we can infer but not witness, questions we can ask but not yet answer. And perhaps that's enough, to know that such places exist, that the universe contains depths we haven't plumbed, mysteries we haven't solved, experiences beyond the reach of any observer, is itself a kind of wonder. Black holes are not just objects in space. They are invitations to humility, reminders that for all we have learned, there is always more we don't know. Questions waiting in the darkness, answers hidden behind horizons we may never cross. The fall into a black hole, whether real or imagined, is a journey toward those questions, a descent into the places where physics becomes uncertain and reality becomes strange. It's a voyage no one can take and return from, a one-way path into the most extreme environment the universe can offer. And in that extremity, in that finality, there is something profound, something that speaks to the limits of knowledge and the enduring mystery of existence itself. What you would see, what you would feel, what you would learn in those final moments remains unknown, and maybe it always will.